Our problem: investigate sigmoidal population growth for snails in a small pond with different values of the base growth rate R and the pond's carrying capacity K. It is important to note that snails require only 1 week to mature from newly laid eggs to reproductive adults, so the change in population depends on the population of the week prior. To solve this problem, we will be using the formula additional snails equals R, the growth rate, times previous population, times 1 minus the previous population over the carrying capacity K. We want to investigate what happens to the number of additional snails as the previous population approaches the carrying capacity K. In order to answer this question, we will use our formula in a Google Sheets form to calculate the number of additional snails over a period of 52 weeks. When growth rate is only 20%, the number of additional snails increases to 997 snails by week 52, a number just barely below the carrying capacity of 1,000. As you can see from the spreadsheet, when growth rate is set at 50%, 100%, 250%, and 350%, the number of additional snails exceeds the carrying capacity of 1,000 snails. When R is 50%, the carrying capacity is met by week 26. When R is 150%, the carrying capacity is met by week 11. When R is 250%, carrying capacity is met by week 8. And when R is 350%, the carrying capacity is met by week 7. Based on these results, we can conclude that as growth rate increases, the number of additional snails increases as well. Furthermore, as the previous snail population approaches carrying capacity, the number of additional snails exceeds carrying capacity. Here we see a graph where the growth rate is 20%, the carrying capacity is 1,000. From this graph, we can see that it closely resembles the sigmoidal or S-shaped graph. This graph has increases until it reaches a maximum value around 500 snails, and then begins to decrease as it approaches carrying capacity. Here we have the same graph, only when growth rate is increased to 50%. As we can see, this graph somewhat resembles sigmoidal growth, however, it hits carrying capacity and levels off. Here we have when growth rate is changed to 150%. The graph starts out looking like an exponential growth, however, it reaches carrying capacity at 1,000. Here we have growth rate set at 250%. The graph starts out looking somewhat like exponential growth, but exceeds carrying capacity. Then the graph starts to do an increasing-decreasing pattern. Finally, we see our graph at 350% for R. Here we see that the graph starts out as an exponential growth. However, when it reaches carrying capacity, it drops to 0 and then continues. As you can see from sheets, when we increase the carrying capacity of the pond to 1 trillion, the number of additional snails does not even come close to reaching the carrying capacity by week 52. As you can see, on week 52, the number of additional snails is just over 100,000. When we graph the number of additional snails at a growth rate of 20% and a carrying capacity of 1 trillion over a span of 52 weeks, we see that the graph does not reach a maximum and start to decrease as it would if it resembled sigmoidal growth, which we saw before. Instead, the graph appears to be exponential growth as the growth starts slow and then speeds up and does not reach a limit or a carrying capacity. This occurs because the growth rate is so small at 20% and the carrying capacity is so large at 1 trillion. To investigate the reasoning behind the instability that occurs with a large growth rate, we change the snail population from a starting point of 10 to a starting point of 999 snails, so that there isn't such a large jump in snail population from start to carrying capacity. We have done this with a carrying capacity of 1,000 snails and at growth rates of both 250% as well as 350%. Here we see the graph when the growth rate is 250% and our carrying capacity is only 1,000 snails. We see that the growth rate or the growth type in this graph is unclear, as it starts at 999 and then does an increasing decreasing pattern. When we change our growth rate to 350% and still start at 999 as our starting population, we see that growth rate increases and then decreases and then increases and then drops all the way down to 0. Although we use sigmoidal growth for all of our analysis, and therefore all our results were sigmoidal by definition, when we look back at the data collection, it is clear that when we have a carrying capacity of 1,000 snails and a growth rate of 20%, as well as a starting population of 10 snails, the graph most closely resembles a sigmoidal S-shaped model. This occurs because our carrying capacity is set high enough at 1,000 and our growth rate is set small enough at only 20% so that the growth in snails is able to increase until a maximum value and then start to decrease as it approaches carrying capacity. This makes